In this section, we're going to be looking at hypothesis testing for proportions. Now, we've already done a lot of this work in our previous section about hypothesis testing overview, so some of this will be familiar. To get started, let's go ahead and look at the steps to the p-value approach to hypothesis testing one more time. The first step is to state HO and HA. And of course, H1 is the same as HA. The second is to state the level of significance. Now, the level of significance is also given as my alpha value. And remember, it's the probability of a type 1 error. Step 3 is I will calculate the test statistic. Now, in this particular section, I have one test statistic that I will be using for each of the problems. So the test statistic in this case is Z equals P hat minus P divided by PQ over N square root. So this is the test statistic that I'm going to be using, and this is distributed normal 0, 1. So when I'm using my calculator, I can use my inverse normal or my normal CDF, and if I'm using tables, then I can use my normal tables. So this test statistic is specific for this case when I'm using proportions. The next thing I would do after I calculate the test statistic is I would calculate the p-value. Now, the p-value is based on this test statistic, so calculate the p-value based on the test statistic. So in order to calculate this p-value, I need to know Z, and then I also need to know the direction of my test for my alternative hypothesis. Step 5 is to make a decision, draw a conclusion, and the only two decisions I can make are to reject HO or fail to reject HO. Those are my only two options. My last step is to summarize in terms of my alternative hypothesis and in terms of the problems. So I have to make sure I always bring this back to what the question was asking. So these are the guidelines that we're going to be following in our problems today. So let's go ahead and put up our first problem. So in our first problem, we have in 1997 a survey of 920 households. So right away, this is giving me some information. This is n equals 920 then, n is my sample size. It shows that 159 of them use email. Okay, so this is basically my number who use email. That's my number of successes. Use those sample results to test the claim that more than 15% of households use email. So this 15%, this is my HOHA business. And it says more than. 5% level of significance is alpha equals 0.05. So using this information, let's go ahead and get started running through this step by step. So my first is to state HO and HA. So HO, I have proportion, or percentage, is equal to, we're claiming that it is more than 15%. So my null hypothesis is always the equal sign. My claim will be in the alternative hypothesis. So more than 15% comes down here. My second step is to state my level of significance. So in this case, alpha equals 0.05. Now my third step is to calculate the test statistic. So my test statistic is Z equals P hat minus P, and then I have square root of PQ over N. Now P hat is given to me up here in this information. It's not given to me directly, but the information in order to find P hat is given. So P hat is the number of successes. In this case, I'm counting those who use email. 159 over 920. Boy, these numbers seem really low for the year 2015. Now, P comes from my null hypothesis, and it's 0.15 from here. And then I have over the square root of 0.15. Q is the complement of 0.15, which is 0.85, because it forces it to sum to 1, and my sample size is 920. Okay, so let's go ahead and plug this into our calculators and see what we get back. The important thing to remember is this entire numerator needs to be in parentheses. So we'd start with parentheses 159, and we don't want to round this, so we don't want to find a decimal approximation for the 159 divided by 920, so I'll just put it in as a fraction, minus 0.15. So that entire numerator has to be in parentheses, and then divided by the denominator with my square root, which would be 0.15 times 0.85 divided by 920. And if you want to put some of this in parentheses, you can, but you don't have to. What has to be in parentheses is that numerator. So when I calculate this, I have 1.9389 for my value. So I'll pop this into our lecture and we'll see where that comes from. Now usually there'll be some directions in my math lab that will ask you how to round it, and with a test statistic they usually say round it to 3 places. So we can see here that this would round to 1.94. The 3 would round up, so this is 1.94. So again, this is my test statistic. Okay, step 4. Calculate the p-value. Now in order to do this, I need to know my test statistic, z equals 1.94, and I need to know, was this a right tail, left tail, or two-tail test? And I can see from right here that this is a right tail test from the alternative hypothesis. So this is a right tail test. Now the easiest way to calculate your p-value is to draw a picture first. So the picture follows after my normal distribution. The mean is 0. Here I am at 1.94, and my right tail test says I'm looking for this area to the right. So this is my p-value, whatever this area is. So if I want to find my p-value, I can go back to my calculator, and I'm going to go to second DISTR. I'm using my normal distribution, so I have my normal CDF here. And my lower bound is 1.94. My upper bound is some really, really large number going toward infinity, like 100,000. My mean is 0 and my standard deviation is 1. So that gives me my p-value. We'll paste that in as well. So we can see from here that my p-value is 0.026189. Now usually they ask us to round our p-values to either 3 or 4 places. Let's go ahead and round this one to 3, 0.026. So 0.026 would be to 3 places. Now if we use our normal tables, we're going to get a slightly different result. So let's go ahead and look at our normal tables as well. So for my normal tables, I want to look up 1.94. And that's going to be the area to the left. So if I look up 1.94, I'm actually finding more area than I need. So 1, 2, 3, 4. So I get 0.9738. And so for my normal tables, that would be this area right here, 0.9738. And then if I wanted to find this area using my normal tables and not my calculator, the shaded area, I would take 1 minus 0.9738. And you can see here I get 0.0262. Okay, so using my tables, I get 0.0262, and then I would round to 0.026. Rounded. So I get my same value after rounding for this one. Now it doesn't matter if you use your normal or your calculator, you should be able to duplicate the solutions in my math lab. Okay, next we're going to make a decision. Now remember, I can only make 2 decisions. I can reject HO, and I would do this if P was less than or equal to alpha, or I could fail to reject HO if P was greater than alpha. So for our case, our p-value is pretty small. It's 0.026. So for us, P is equal to 0.026. And then we also had an alpha that was given. So let's go ahead and look back up and see what that alpha level was. So we can see here that alpha was 0.05, or 5% level of significance. So alpha was 0.05. So what we have then is we have P is less than or equal to alpha because 0.026 is less than or equal to 0.05. So our decision would come up here would be to reject HO in favor of HA. So that's our decision. And we would say this because my p-value is less than or equal to alpha. Now my next step would be to make some sort of a conclusion here. Or summarize our results. Now we have to be careful how we summarize this. So we were saying that we're testing to see if the proportion of people who use email is more than 15%. Okay, so we rejected HO, so we have support for HA. So I would say the data supports the conclusion that more than 15% of households use email. So again, we always blame it on the data. The data supports or the data does not support the conclusion. So what we're looking at then is saying that we have support for the alternative hypothesis, which is more than 15% of the households use email. Now another concern I would have about this particular study is whether the data is even valid anymore. 1997 was almost 20 years ago now, and certainly email use in households has changed rapidly. So I'm not sure if our population is the same in terms of internet usage as it was back in 1997. So I'd be a little skeptical about these results, but they do seem to indicate in the correct direction that more than 15% use email. Let's go ahead and look at another example. Okay, so as usual, it's important to identify some specific information. So on this example, it says in a recent poll of 750 randomly selected adults. So that means what we have here is our sample size. So 750 is our sample size. This is N. So in a recent poll of 750 randomly selected adults, 586, so this is our ones that we're counting, this is our number of successes, said that it was morally wrong to not report all income tax on returns. So this was based on our survey. So my information that I can get from this is p hat. So for my p hat, I would have 586 over 750. And I'm just going to leave that as is. I'm not going to divide that out or round anything. And then from here, it says use a 1% level of significance. So my alpha level is 0.01 to test the claim that 70% of adults say that it's morally wrong to not report all income tax on returns. So this is going to be my HO and my HA information. So let's go ahead and get started with our first step, HO versus HA. So we're talking about proportions here, percentages. So I'm trying to test to see if 70% of adults say that it is morally wrong to not report all income on tax returns. This is versus the alternative that not 70%. So if I'm trying to test the claim of equality, the complement of that would be inequality. My second step would be going ahead and listing my level of significance. My third step would be to go ahead and calculate my test statistic. And my test statistic for this case is Z equal P hat minus P divided by PQ over N square rooted. So P hat comes from right up here, 586 over 750, and again I'm not going to divide that out or round it. My P comes from my null hypothesis, which is 0.70, and then my denominator would be the square root of 0.7 times 0.3, because P and Q are complements of each other. P is equal to 1 minus Q and Q is equal to 1 minus P. and then n is 750. So let's go ahead and plug this into the calculator and see what we get back for a value. So as usual, we need to have parentheses around my exponent. 586 divided by 750 minus 0.7. Okay, so that's my numerator. I'm going to divide it by the square root of 0.7 times 0.3 divided by 750. Now all this is underneath the square root sign. So what do I get for my test statistic? I get 4.86, and let's go ahead and add this to our lecture as well. So for my calculator results, I get that this is 4.86 standard deviations above the mean. That's a long way, because remember, that's what a z-score is the number of standard deviations I am above the mean. So that's my test statistic. Next, we want to go ahead and calculate our p-value. Now, in order to calculate the p-value, I need to know my z-value, my score, my standardized score, and I need to also know the direction of the test. Now, the direction of the test is my alternative hypothesis, and this is a two-tailed test. Now, when I have a two-tailed test, that kind of reminds me that I have to double my probability. So the easiest way to calculate your p-value is to go ahead and put up a curve sketch. I know my mean is 0. 4.86. So this shaded area that's more extreme than the 4.86 is half of my p-value. It's half because I have a two-tailed test. So if I want to find this value of 4.86, I could use my calculator. So let's go ahead and try that option first. And that would be under second DISTR, normal CDF. The lower bound would be 4.86. My upper bound would be this 100,000. My mean is 0 and my standard deviation is 1. So I get a very, very small number here. Now this is written in scientific notation, so we have to make sure that we interpret that correctly. So this is 5.8 773567777, and this means times 10 to the negative 7. So what I would do, starting at this decimal, I would move it 7 places to the right. So there's 1, 2, 3, 4, 5, 6, 7, and then all of these are zeros. So if I were to talk about my p-value, this is my p-value. It's very, very small. Now if I were asked to round this to 3 places, this would be 0.000. If they asked me to round it to 4 places, it would be 0.0000. Because my first significant digit doesn't even come up to the 7th place, and then it will finally show up. So half of p is 0. And that tells me that the p-value is going to be 2 times that, which is just approximately equal to 0. Because this is approximately equal to 0 just because of rounding. Okay, so now let's go ahead and look at our decision that we'll make. And remember, I only have 2 decisions. I can reject HO and I can fail to reject HO. If I reject HO, that's when P is less than or equal to alpha. Fail to reject is P greater than alpha. Now remember, for us, my P was approximately equal to 0. And my alpha, my level of significance, was given to me in the problem to use as 0.01. So my alpha is equal to 0.01. Now I just go ahead and compare these two things. So when I compare these, my P is definitely less than or equal to alpha. 0 is less than or equal to 0.01. So my decision would be to reject HO in favor of HA. Okay, so that's my decision. Next thing I'll do is I'll write a summary or a conclusion. And we always blame it on the data. So the data. Now we rejected HO here. So that means I have support for the alternative because I rejected HO. So I have support for the alternative that the proportion or the percentage isn't equal to 0.70. So the data supports the conclusion that the percentage of adults who say that not reporting all of your income on your taxes is not equal to 70%. That would be one way to say our summary. Now there's a lot of different ways that we can say that. So be really careful how you write these summaries. I always blame it on the data, so the data supports or the data doesn't support the conclusion, and kind of carry through from there. But again, be very careful about how you write those. Okay, on the next example, we're still working with percentages and proportions, but we'll see on this one it's really particularly important that we don't do any rounding at all because our numbers are so large and then small at the same time when we divide them out. So to get started, it says in a study of 420,071 cell phone users. So this right away tells me my sample size, 420,071. 138 of the subjects. So this is telling me my number of successes, so this is going to help me determine p hat. 138 subjects developed brain cancer. Test the claim that the cell phone users develop brain cancer at a rate that is different from, so that tells me in my HO right away I have p not equal to the rate of 0.0340%, and then use my level of significance, which is very, very small here, of 0.005. So to get started, p hat is going to be my number of successes over my total sample, and I don't want to divide this out because if I do and I round, it's going to change my number. So I just want to keep this as is. And again, my level of significance here is 0.05. So let's go ahead and get started by stating HO and HA. So HO versus HA. Now my proportion that I'm looking at is 0.03400. So the P would be 0.000340. I'd move my decimal 2 places to the right to convert this to a decimal from a percentage. So this would be 0.00340. Remember, these are very, very small numbers, so we have to be careful about this. Now this means different from, so this is my not equal to case. The equality always goes with my HO. Second step is to state my level of significance, which was very, very small here. It was 0.005. Third step, we're going to calculate our test statistic. Now with our test statistic, it's good just to write it down first and then go ahead and populate it. This would be p minus p hat, or sorry, p hat minus p, pq over n square rooted. So my p hat was right from up here, 138. Divided by 420,071 minus the proportion in my HO. This is 0.000340. Now this one's going to be a little tougher because I'm getting some strange numbers here. 0.000340. Now Q is going to be 1 minus that. So let's go ahead and pop open our calculators. So it'd be 1 minus 0.000340, and I get point from up here 0.99966. Now we don't want to round any of this because if we round anything it'll end up creating some error or introducing error into the problem. 420,071, and this is all square rooted in the denominator. So to find that z value, we go ahead and plug it into our calculators. Has to be parentheses around the numerator, so 138 divided by 420,071, and that's in parentheses, minus my hypothesized proportion, which would be 0.000340, divided by the square root then of 0.00034 times 0.99966 divided by my sample size of 420,071. This is all underneath the square root sign. So it looks like to me we get a value of negative 0.40373. Negative, better make sure that negative is easy to see. Negative 0.40373. Now if they ask us to round this to 2 places, I would round this to negative 0.40. If they ask me to round this to 3 places, it would be negative 0.404. If they ask me to round it to 4 places, you kind of get the idea. So you kind of have to look at the directions in my math lab to see how they want it rounded. So that is my test statistic. Next thing I do is I want to calculate my p-value. Now to calculate my p-value, I need 2 things. I need my z-score, and I'll round this to 2 places. And I need to know if this is a right tail, left tail, or 2-tail test. That's always in my alternative. This is a 2-tail test. So this is a 2-tail test. Okay, quick little picture always helps us out here. So here is my negative 0.40. And I'm looking at a 2-tail test, so I'm looking as extreme or more extreme. And since it's a 2-tail test, I have to make sure I double my p-value. So here that I'm finding is only half my p-value. Let's go ahead and use our calculators to find that area. So I do second DISTR. This would be my normal CDF. My lower bound is a very negative large number, so maybe negative 100,000. Up to negative 0.40 would be my upper bound. And of course my mean is 0 and my standard deviation is 1. So for here I get 0.344578, let's say. 0.344578. Now my true p-value is equal to twice that because I have a 2-tail test. So I'd have 2 times 0.344578. Okay, so back in my calculator, I already have the 0.344578 here, so I'm just going to hit times, and it'll take my last line and times it times 2. And here is what I get for my answer. Okay, let's go ahead and put that in. And we can see from here, if we round this to 4 places, I get 0.6892. That's a big p-value. Okay, now if you use your normal tables, this is going to look a little different. So let's go ahead and grab our normal tables. So we're trying to look up, if we look from our picture, negative 0.40 and finding the area to the left. So here's negative 0.40, 0.3446, and then I would double that, and I'd get something very, very close to my value as well. So if you're going to use your normal tables, you get 0.3446, and then you double it, and you get doubled 0.3446 times 2, and we get 0.6892, which this would round to 4 places the same. Okay, so it's good to use your normal tables as well. Next step is to make a decision. Now remember, there's only 2 decisions we can make. We can reject HO if P is less than alpha, less than or equal to alpha, or we can fail to reject HO if P is greater than alpha. Well, let's remember what we have for my p-value. It's a pretty big number. I have P equals 0.6892, and my value for alpha was very, very small. It was 0.005. Remember, that was given. Well, we can see pretty clearly here that P is greater than alpha. 0.6892 is greater than 0.005. So our decision here should be to fail to reject HO. Fail to reject HO. So that means that my alternative hypothesis really doesn't have much support. So here's my summary. Now remember, this was about cell phone users. Fail to reject HO. So the data does not support the alternative hypothesis. The data does not support the conclusion that the proportion of cell phone users who develop brain cancer is different from that of non-cell phone users. So it looks like there's not a statistically significant difference between the cell phone users and the non-cell phone users. I would just like to go ahead and look up real quick at this negative value. So what this is saying, if we think about it, this is cell phone users minus non-cell phone users. So it looks like to me non-cell phone users have a slightly larger developed at a percentage, a slightly larger percentage of brain cancer developments. But it's not enough to be statistically significant. So if they were trying to check to see if cell phones cause cancer in this study, basically, it actually ended up being slightly the other way. So again, you have to look carefully about where you have support or not support based on those conclusions. As usual, if you have any questions, please bring those to class or stop by during my office hours, or you can also check out the Math Center at the library for help. Good luck on this assignment.